Hello everyone, I am Dr. Saurabh Saxena and today's topic of discussion is the solution of one-dimensional heat equation. Before going ahead, the two questions in our mind comes. Number one, what do we understand by one-dimensional heat equation? And number two, what do we understand by solution of this equation? One-dimensional heat equation is given as del U by del T equals to C squared del 2U by del X2. I just gave the name equation number 1, and to understand this equation, let us consider the heat flow in a rod of metallic body of a conducting material. Assuming the lateral surface of this body are insulated and no heat is allowed to transfer from any of the ends. Considering one end of this body at origin, we can understand the point X equals to A may be considered as at a distance of A units from first end. Now, the solution of this particular differential equation is known as the relation between the dependent variable and the independent variable. Here in this differential equation, the x, small x, it denotes the position of a point on this metallic body. The small t, it denotes the time at which we have to find the temperature, and u, small u, it denotes the temperature at any point at any given time. The solution of this particular differential equation is taken as u equals to x into t. Now, if this is the solution, it will satisfy the given differential equation number 1. So, and for that, we are just calculating the value of del u by del t. Del u by del t means to differentiate u partially with respect to t, and for that, capital X will be a constant and the differentiation will be held with respect to small t, and we get x dt by dt. Here del is converted to d, as it was earlier assumed that capital X is only a function of small x and capital T is only a function of small t. In a similar way, we are just finding del u by del x, we get t del x by del x, and differentiating one more time partially, we get del 2u by del x2 as t del 2x by del x2. Again, we will write d instead of del, as capital X is again also only a function of small x. Now, we will satisfy the given equation number 1 by these values. We get, we are just putting the values of del u by del t, del 2u by del x2, and we are getting this relation. Now, just separating the variables, we get 1 by x d2x by dx2 equals to 1 by c square t dt by d small t. Here, the important point is this. Now, left hand side, it is differentiation with respect to small x. So, it will either be a function of x or it will be a constant. Similarly, the right hand side, it is a function of t or a constant. Function of x and function of t may not be equal. The reason is x and t, small x and small t, are taken as independent variables. So, there may not be any relation between x and t. The only result we get is both the sides, left hand side as well as right hand side, will be constant. So, we are taking it as k. Now, this is relation number 2. After here, we are just having 3 possibilities of this relation, because the both two sides are equals to a constant, and a constant may be 0, may be positive and may be negative. And to discuss this, we will consider all the cases. Case number 1. If k is equals to 0, if we are taking k equals to 0, then we get 1 by x d2x by dx2 is equals to 1 by c square t dt by dt equals to 0. Solving this equation, we get 1 by x d2x by dx2 equals to 0, and it implies x equals to c1x plus c2. As the left hand side is a second order derivative, the solution will be given by just integrating 2 times. Also, when we take the term of t equals to 0, here we get the solution as C3. And finally, the solution of equation number 1, that was the heat equation, is given as u, which is a function of x and t, equals to c1x plus c2 into c3, and in a more simplified way we can write it as ax plus b, where a and b are 2 new constants obtained by multiplying c1 and c3 and c2 and c3. This is the solution which we get when we take the value of this constant k equals to 0. Again, case number 2. If k is negative, that is, we may take k equals to minus p square. If k is equals to minus p square, then again from equation number 1 we get now taking the term of x with minus p square, we get the value of x as x equals to c1 cos px plus c2 sin px. Again, if we take the term of t, we get t equals to and the complete solution of equation number 1 may be given as u, which is a function of x and t, is equals to c1 cos px plus c2 sin px into c3 e to the power minus c square p square t. We have dealt 2 cases, case number 1 when k was 0 and case number 2 when k was negative. Now again we are taking k to be negative or positive. We are going to deal with case number 3. If k is positive, that is k equals to plus p square. If k equals to plus p square, then from equation number 1 we get 1 upon x d2x by dx2 equals to 1 by t c square t dt by d small t equals to p square. It implies 1 by x and it gives the solution as x is equals to c1 e to the power px plus c2 e to the power minus px. This solution may be obtained just by solving this equation as constant coefficient, second order differential equation with constant coefficient. we'll be doing this by taking the help of auxiliary equation, and we'll be getting the same result as I have written here. And it implies T is equals to C3 e to the power C square P square T. And the solution of equation number 1 is u x comma t is equals to C1 e to the power px plus C2 e to the power minus px into C3 e to the power C square P square T. See, here I am writing u as a function of x and t. It is quite clear from the given differential equation. Del u by del t equals to c square del 2u by del x2. Here u is the dependent variable and t and x are the independent variables. So obviously u will be a function of x and t. In this way, we have got three solutions of one-dimensional heat equation. Actually, the solution of one-dimensional heat equation means to find the expression for u as a function of x and t, where I have already told x denotes the point on the metallic body and t denotes the time at which we have to find the temperature. So here we have got three expressions for the temperature distribution function. One is this, second and the third. Out of these three solutions, the point is what should be taken as the appropriate solution for this equation number 1. Since this equation is one-dimensional heat equation and it has its own physical significance, and its own physical significance states that if it is the heat equation, that as per the significance of heat flow, as the time increases, the value of the temperature should decrease. So out of these three solutions, whichever is satisfying this physical behavior of heat flow, that will be taken as the appropriate solution for this differential equation number 1. So now we are considering just one by one case. Here, case number 1. It simply shows that the temperature is equals to Ax plus B. It denotes that it is not a function of T. So it may not be a solution of heat equation. Case number 2. It denotes C1 cos Px, C2 sin Px, C3 e to the power minus C square P square T. If the time increases, then definitely the exponential power of E, exponential powers, it will increase but in the negative axis. So the negative powers will be increasing and e to the power negative infinity approaches towards 0. That is, if time will increase to infinity, this expression e to the powers minus c square p square t will decrease and it will approach to 0, and hence it may be taken as the solution as it satisfies the physical behavior of one-dimensional heat equation. Case number 3. Here we are getting e to the power c square p square t with positive sign. It simply implies that if the time will increase, this particular term e to the power positive powers will increase, and then this particular term will increase or it will approach towards infinity. So from third solution we are getting that if the time increases, the temperature will also increase. So solution number 3rd may also not be taken as the appropriate solution for the given heat equation. Hence we can consider the case solution corresponding to case number 2 as the solution of one-dimensional heat equation, as it satisfies the physical behavior or physical nature of heat flow. Now also I would like to mention one more thing. This case number 1, it is also of a certain importance. What is the importance? Case number 1 simply denotes that uxt equals to ax plus b. That is, it is not a function of t. It is not a function of time. And whenever the temperature is not a function of time, the temperature of a body is not increasing with respect to time, it will be taken as in the steady state. Because the steady state is the state at which the temperature stops varying with respect to time. Hence, this solution number 1 corresponding to case number 1, that is k equals to 0, will be taken as the solution of one dimensional heat equation in steady state. So out of these three solutions, the two solutions are of utter importance. Number one, this is the solution when temperature depends on time, and this one, it is the solution when temperature does not depend on time, that is in the steady state temperature.